So in this video, we're going to take a look at deriving the equation of motion for the simple system shown here on the left-hand side. This system consists of a mass connected to a spring, which is then connected to a fixed reference point. This block has a mass of m, which is expressed in kg, and the spring has a stiffness of k, that's expressed in newtons per meter. And another point of note about this diagram is we've labeled the positive sense of the displacement as being downward, and that will help us pick the right direction for our resultant force when we draw our free body diagram. But let's take a look first of all at some of the assumptions that we're going to make during this problem. So the first assumption is that we have linear springs. And what this effectively means is if I were to draw out a set of axes, and on this axis I'll label it as being the spring force in newtons, and this axis I'll label as being the extension of the spring in meters. What this assumption is stating is that there's a linear relationship between force and extension. So basically the spring is operating in its linear range. Now, what is true is that most springs, if they're extended beyond a certain limit, they actually result in a non-linear relationship between force and extension. So we're basically assuming that our spring is extended within this range, or not beyond this range. And this slope in here is k. We're going to call that k for our stiffness. And what this means is that our force can be expressed as k times the extension of our spring. The second assumption that we're going to make is that the springs are massless. And again, that's to make the derivation easier. And the third assumption that we're going to make is that there is no damping in the system. So effectively what this means is that our response against time, if we label this axis as our vertical displacement and this axis as our time, our response will look something like this. So effectively our amplitude from a given set of initial conditions will be constant. Whereas a damped response would look something more like this. Effectively, our displacement over time is trailing towards zero. So in these types of problems, you'll often hear the term x is measured with respect to the equilibrium position, or the distance or the displacement of the block is measured with respect to the equilibrium. And let's just take a look at what that means. So imagine here we have our ceiling where our spring is attached, and imagine we don't hang anything onto the spring. So effectively the spring is just dangling free from the ceiling. That spring is going to have a length of f0, and f0 stands for our free length. Now, imagine we hang a weight onto the end of that spring. It's also worth noting that at the free length of the spring, there's no tension in the spring, there's no force in the spring. But now there will be, because we've added a weight onto the end of this spring. And let's call the amount by which that spring extends beyond its free length xe, for x extension. And here we have our mass. If we take a free body diagram of the system at this point, we'll have our mass, and we'll have two forces acting on the mass. We'll have a spring force acting upward with a magnitude of our stiffness multiplied by the extension, which is just kxe, and we'll have a force due to gravity with a magnitude of mg. Because our system is in equilibrium and our mass is completely stationary, these two forces have to cancel. So effectively we end up with kxe minus mg is equal to 0. Now, let's consider if we deflect the spring by another amount, so that the mass is moving. So let's redraw our diagram. And let's imagine that our spring has been deflected by an additional amount. Let's call that x, and let's call this position in here xe, and this length in here f0 for our free length. So at the free length, there's no tension in the spring, but when we redraw our free body diagram, we have our force acting upward on the mass and our gravity force acting downward. So the magnitude of the upward force is just going to be our stiffness again, multiplied by xe plus x. And the magnitude of our force acting downward is just going to be mg again for the block with a mass of m. However, the forces this time don't cancel because the mass is moving. There's a net acceleration in one direction. So effectively, we end up with a resultant force. This is following on from Newton's laws that states that the sum of the forces is equal to mass times acceleration, which in our case is just the mass times by the second derivative of our displacement, or the second time derivative of our displacement. So because we previously labelled x as being positive downward, we'll say that the resultant force, mx double dot, is also acting downward. And when we go to sum our forces, it's very important that we sum the forces with positive forces being in the direction of the resultant force and negative forces being in the opposite direction of the resultant force. So for example, mg will be positive. However, it'll be minus k times xe plus x. And all of that is equal to the mass times by the second time derivative of x. And if we just clean this up a bit, now previously we stated that kxe minus mg is equal to 0, which means that minus kxe plus mg is also equal to 0. So what effectively happens is these cancel out because they're equal to 0, and we're just left with mx double dot plus k times x is equal to 0. And we're just going to clean that up by dividing both sides by m, and we end up with x dot plus kx over m is equal to 0. So what this effectively means is that if you're measuring the displacement of your mass with respect to the equilibrium state of the system, and therefore the equilibrium length of the spring, you don't have to consider the weight force or the tension in the springs due to the weight force when drawing out your free body diagram. So effectively, it results in a more condensed free body diagram, where the only force you need to include is the k times x force acting upward, and the resultant that we said is acting downward with a magnitude of mx double dot. Now in the previous video we took a look at the pendulum example, and we derived the equation that describes the deflection of the pendulum over time. But we started out with an equation of motion that looks like this. And what you should see is that these two equations are very similar. The only difference being in this equation we're solving for theta, and in this equation we're solving for x. And in this equation we have a g over L in front of the theta, whereas in this equation we have a k over m in front of the x. So from this, we can essentially use the analysis that we performed in the previous video to tell us some things about the system that we're looking at. So in the pendulum example, omega n was equal to square root g over L. Therefore, in the spring mass example we're looking at, omega n is equal to the square root k over m. In the pendulum example, the initial conditions were theta naught, omega naught, whereas in the spring mass example, the initial conditions are going to be x naught and v naught. And in the pendulum example, the equation that described the angular deflection of the pendulum over time was given as the theta naught squared omega n squared plus omega naught squared all over omega n multiplied by sine square root g over L times by t plus tan inverse theta naught omega n over omega naught. So by that logic, the equation that describes the movement of our mass on the spring is just going to be the square root of x naught squared omega n squared plus v naught squared over omega n times by the sine square root k over m times t plus tan inverse x naught times omega n over v naught. And the only difference here is that omega n is the square root of k over m. And that is the equation that describes the response of the system over time for this particular system under consideration.